Well, welcome back, everybody. Hope everyone had a good week. This is our third week. Our plan for today is to finish up chapter 2, finish chapter 3, and then go be done for the day. And then Wednesday, I did move the exam to give you a little time to get ready for it. Some of you opted to keep it on Saturday. That's fine. If you still want to do it on Saturday, let me know so I can open it up for you on Saturday. But let me know for sure. Okay. Let us just jump right in there. Any questions before we begin? No questions? Okay. All right, so we ended up on this slide right here. What we were doing is learning how to convert numbers to scientific notation. Scientific notation is just an alternative means to input into your calculator or to write very large numbers or very small numbers. Okay, and in this example, we have 548.005. When you have a number and you need to convert it to scientific notation, note the number of sig figs that you have, significant figures, because your number should have the same number of sig figs that you start off with. Okay, and so memory, we got all of these here, all sig figs, all significant. Refresh your memory on determining what is significant and what numbers are not significant. So we got 6 significant digits. We're number 1. Number 2, we have 3. All the integers are. The zeros are not significant with respect to they're significant with respect to value, obviously, but they're not significant with respect to accuracy in your number. Okay, it's all about presenting your final data, your final number, with the least accurate number of digits that was used to do what mathematical function you had to do to get to that number. Okay, you can't be more accurate than the least accurate digit that you used. Okay, so we have 3 sig figs, and notice that we had 3 sig figs in our answer right here. And then here we had 3 sig figs again. These zeros up front are leading zeros and therefore not considered significant with respect to significant digits. And a thing to remember is use those 2 questions. 1, is there an integer? Now, this is only with respect to zeros. Is there an integer in front of these leading zeros? And the answer is no. And you got to know right away, these are not significant. Ask the same questions for the zeros behind the 4. Yes, there is a integer in front of those zeros. Talking about these right here. There's a 4. And there's a decimal point in that number, anywhere in that number. Therefore, those zeros are significant. Okay. So you have 3 sig figs there. The last one, number 4, again, ask your question with respect to the zeros. Yes, there's an integer in front of them, but no, there's no decimal point. Therefore, they're not considered significant. Okay. And now it's a matter of moving, writing the number, finding the decimal point, and then with the number greater than 1, we're going to go from right to left, which tells us we're going to go here, and we count the number of decimal places, and we keep going from right to left until we land in front of the last integer. Okay, the last integer, which in this case is a 5. And so we write out 5.48005, and then times 10 times the time symbol, and then 10 and the exponent to which represents the number of decimal places that we move from where the decimal point was to the last integer going from right to left. Okay, the same scenario here. The decimal point, obviously, as you know, is at this point. Okay, so we count the decimal point places, and that's 1, 2, 3, 4, 5, 6, and 7. We got to go 7 decimal places from right to left. So that's the exponent. Our number 6.8 times 10 to the 7th. Now, this is just another way of writing, like, for example, times 10 times 10. Okay, it's just this exponent is just a shorthand method of writing all those 10s. Here we got 7 of them. Okay, now these first two numbers are positive, number greater than 1. The exponent is positive value. When we get numbers less than 1, like number 3, and we're going to move our decimal point from left to right. So we go 1, 2, 3, and 4. We find the first integer and we stop right behind it. That's it. Okay. And that becomes 4.00 because there's 3 sig figs times 10, and that becomes a -4. The exponent is a -4. Okay, because we're going from right to left. And then the last one is 2 times 10 to the third. So we went through that scenario, and as a quick refresher on that. Now, how do you input this number into your calculator? Okay, now it depends on your calculator. I've not seen any new button, but as far as I know, there's only 3 types of buttons that allow you to put input into your calculator a value into scientific notation. Okay, there. If we look at the first calculator here, it's got a square box. Got a few people coming in. Okay, your calculator, depending which one you have, the newer calculators tend to have this button where it looks like it's a times symbol, X, and then 10 to the X power, okay? All right, that is your scientific notation button. Now, not to be confused with the button, and some calculators have that, as 10 to the X, okay? Not that button, but has an X in front of it times 10 to the X. Other calculators have a double E button. So this one in red right here has the letters EE, okay, EE. And then the other third example, they may have the letters EXP, okay? And the one in white here, this one I'm showing down here, this is the scientific calculator for Windows 10. But there is an EXP. So there's 3 types of buttons, depends on your calculator. These buttons are how you input a scientific notation value into your calculator. Now, another button that you should be aware of on your calculator is a toggle button that converts that number you inputted either to a negative and toggle it back to a positive. So if I input the number, I hit that button and make it a negative. And this is where you need, for example, if the whole number is a negative, you need to input that, hit the toggle button. Or if the exponent is negative, you need that toggle button. On the Windows calculator is a button that says plus / minus. It's just a toggle. It flips that number back and forth from positive to negative. Okay. On this one and here, it's this button. It's hard to see, but you can see the plus minus. Yeah. Okay. And then on this other calculator, I'm circling it. You just have a negative in brackets. Those are your toggle buttons to make that number either positive or negative, back and forth, back and forth. Okay. So those are the buttons you should be familiar with, because we're gonna practice inputting very large numbers into the calculator. Now, once you input that number into the calculator, okay, now you do the mathematics like you normally would. You're not doing this, nothing special. You're just a big giant number. You're still going to multiply or divide or add or subtract, whatever you're going to do to it. Okay. So there's nothing magical about this. They just put in a big number. And so let me share my calculators up. Let me share my calculator, and I'm going to input that number 2.39 times 10 to the 8th into the Windows calculator. Okay. All right, so I'm using the EXP button, and let me clear it up. And so the number was 2.3. So here I can just type in like you normally type in the number 2.39. Okay. Now notice that toggle button. If I wanted to make that a negative, if I click it, it becomes a negative, right? But this is a positive number, so I can just toggle it back. Now, once you input the first first numbers, hit the EXP button. Okay. In the Windows calculator, there's a little E that gets shown on the display. That is to tell you that represents the times 10 part of the scientific notation. This is where now you input the exponent. So in this example, it was 9. So I just type in 9. So this would be representative of 2.39 times 10 to the 9th power. Okay. If I needed to make that a negative 9, that's where that toggle button comes in. This number represents 2.39 times 10 to the negative 9. That's a number less than 1, but it's a positive. So that's how I input that number. Okay. Now, some calculators, you can leave it in, it'll show you the value in scientific notation, or you can put it in long form. So in this case, the Windows has a F, floating point, or engineering units. If I click it, it puts it into the long form too. Okay. Or click it back into scientific notation. Let's see what else. All right. Now, the newer calculators will display that number as if you had written it with the correct scientific notation format. That is 2.39, the symbol times 10 to the 9th power. Other calculators will either give you the letter E, like the Windows calculator does. It does not display the times 10 at all, but just displays the E and then the exponent. That is the notation, the format for the calculator, and you need to convert that back into the correct format with the times 10 to the 9th. Okay. All right. So let's go back. And this is just a blown up. Oh, got a couple of questions here. Sorry, I didn't see that here. All right. And no worries about the lateness. Okay. What about the TI84 calculator? Definitely should have, if you're asking about scientific notation. Anahid, is that what you're asking?
I was able to find it. It was right above number 7. I couldn't catch it at first, but I saw it.
Okay, great. And Andrea, you have the EE function. Okay. Now, in these pictures here, they show the scientific notation button as the primary function. Check your calculator. It could be a secondary function. So these buttons could be in the back. Okay. So to access those buttons, obviously, it's a secondary function. You have to utilize the second button. Like in this case, well, at least I know for sure here in this calculator, you got to hit the second button. If that function is a secondary function and normally is written in the, like here, this is a secondary function written in yellow here. Okay. So check your calculator, see what if it's primary or secondary. And if you're having trouble finding it, take a picture of it, send it to me, and we'll look for it. or check your manual, look under scientific notation, or you can get up online. And I'm sure there's a manual out there someplace. If you don't have the manual, most of us buy a calculator and we end up throwing the manual away. But check the manual. Maybe you can download it and read about how to input scientific notation. Okay. Again, nothing magical here. It's just a means to put a very large number into the calculator. Most calculators, you know, if you start to type that number in manually, won't take it, and you have to actually put it into scientific notation. Okay. All right. Let's see. So it's either primary button or secondary. So use calculator. For the test, I have function the lockdown browser. It should display a calculator up in the menu. But if you don't have one, you know, make sure you have one. I wouldn't use the Windows calculator or you're doing exams, or because if you have to toggle back and forth, Canvas will alert and say, no, you're getting out of your window. Okay. So I would get a calculator. And they're not that expensive. You just make sure they got scientific notation, because we will be working with large numbers when we do some calculations. And so let's take this example here and let's input it into the calculator. So I'm going to take that number, and it is 2.84. So I've got 2.84. Okay, and times 10 to the 23rd. So we hit exponent 23. Okay, and that again is the format of the Windows calculator. The E represents the times 10 to the, let me see if I can write that down. This part right here, this represents times 10 and then to the 23rd. Okay. All right, so now the number is inputted. You can now do the mathematics of whatever you're going to do. And here we're going to take this number and divide it by 7.24. So again, we hit the divide, nothing magical again, okay? And now we input again 7.24 exponent 12, okay? Hit the equal. So now your calculator has this big old number. And let's take it, and we're going to go ahead and copy it, bring it back. And the number we got was this big old number here. Okay, that's the number we got. Now, here we have to keep track of our sig figs, right? We're taking how many sig figs does 2.84 times 10 to the 23rd have?
3.
Okay, 3, you're correct. And how about 7.24 times 10 to the 12th?
3 as well.
Exactly. So our answer should not be more accurate than the 3 sig figs, because the numerator and denominator both have 3 sig figs. So we go to the 3 sig fig position, and that would be right there, right after the first 2. And we look at the number, we do the rounding step like we normally would do, nothing different. We look at the 2, 2 is less than 5. So that 2 remains as 2. So we write 3.92. And now we type in 10 times 10 to the and we use that little caret, which is the Shift-6 button, okay? And we just type that in like that because this doesn't support subscript, superscript. So that little caret, which is Shift-6 key, represents a superscript. And that is our answer, okay? All right. So practice that on your calculator so you come up with that number. And we will be using numbers in the order of 10 to the 23rd power down the road. So all this we'll be using it. Okay. All right. So there's its number. Okay. All right. So if there is a problem, like I said, you're not sure how to use it in the calculator or see or find your button, by all means, take a picture of it, send it to me, and we'll take a look at it. Sometimes some calculators will give their answer in this format, like this. Okay, then maybe that's your answer that your calculator shows. It's not showing the E button, and nor is it showing the times 10 to the whatever power. It just shows it the 8 here kind of superscript. That is not the correct format. Okay, but what the way, if you were to present that data like that, what that means is you take 1.23456 and multiply by itself 8 times. That's not correct. And so convert that format of your calculator back into the format of scientific notation to present that as your answer. All right. So this one here, this little part, you're familiar with this already. I'm not telling you something that you don't already know. Okay, the percent. You know, obviously, if I were to ask you a question, all right, you take a test, 100 points, you got 80 right. What do you get? What's your final score? 80 questions out of 100 right. What grade did you get? Wouldn't that be 80%, right? You got 80 questions, which is the part, divided by the whole, which is a total amount, in this case, 100 questions. You multiply that by 100, that gives you the percentage, okay? We use that quite a bit for a lot of things. So in this example, it says the gold ring has a mass of 239.45 grams. It was analyzed, and it was determined that it had pure gold. The pure gold in it had a weight of 198.38 grams. Question is, what percent of this ring is gold? And so the part is the pure gold itself, which is going to be a number much less than the whole. Okay. And the whole is 239.45 grams. Plugging in the numbers times 100. Okay. You get this 82.84819, et cetera, et cetera. Big old number. You might be tempted to present that number, but that would be incorrect, okay? Because cannot be more accurate than the least accurate digit. You can see the numerator and denominator both contain 5 sig figs, right? So our answer should contain no more than 5 sig figs. And so to find that, we go from left to right. 1, 2, 3, 4, 5. So that means that 8 is our 5 sig fig position. And so everything else to the right is going to be truncated. Okay, now we have to determine, we're going to round that 8 and find out, do we keep it at 8 or round it up? We look at the neighbor, okay, which is a 1. It's less than 5, so therefore the 8 remains as 8, and report that as 82.848%. Okay. All right, that's pretty straightforward. We'll be using that down the road. Okay, that brings us to the end of chapter 2. Okay, we're good with that. And what we did here, kind of introduced some mathematics here, but we're going to actually start doing some calculations. But before I do that, I want to share with you, I believe I sent you this file. It's a PDF file, which has to deal with the metric system. Okay. And in this table here, we got the 3 units that we utilize in the metric system: the mass, the volume, and the length. The units of mass are grams, volume is liters with a capital L, length is meters. Okay. Now, what we have here is conversion factors. We know that 1 kilogram is equal to 1,000 grams. Okay. 1 kilogram is equal to 1,000 grams. Let me change the color here. Guess what? 1 kiloliter is also equal to 1,000 but liters. And 1 kilometer is equal to 1,000 meters. Okay. Because kilo is 1,000 times greater. Now, when we get to numbers less, like for a gram, 1 gram, there are 10 decigrams in 1 gram. One way to remember that, D stands for like decade. Decade is 10 years, right? 10 years in the decade. So therefore, there are 10 decigrams in 1 gram. All right, there are 100 centigrams. C, centigram, the prefix. Centa can stand for century. Isn't there 100 years in a century, right? 100. So there are 100 centigrams in a gram. And guess what? We can translate that over to liters. There's 100 centiliters in a liter. And go further and say, hey, there's 100 centimeters in a meter. Okay. And then milli. There's 1,000 years in a millennium. That may help you, okay? Because we got 1,000 milligrams in 1 gram, which we just move it over to liters, drop the G, add the capital L, and we got milliliters. There are 1,000 milliliters in 1 liter, and there are 1,000 millimeters in 1 meter. Okay. So pretty straightforward as far as prefixes. The one, if you're not familiar with, is this one. It looks like a U with a little tip up front. That is micro. Oh, let me see if I can write this a little better here. Micro. The prefix micro. And micro is a million. Okay. So there are 1,000,000 micrograms in 1 gram, as there are 1,000,000 microliters in a liter, and a million micrometers in 1 meter stick. Okay, you can put that in perspective. You had a meter stick, which is like a yardstick. Okay, so there are 10 decimeters in that 1 meter stick. There's 100 centimeters in that 1 meter. There's 1,000 millimeters in that 1 meter stick. And there's 1,000,000 microliters in that 1 meter stick, to put it in perspective. Now, the takeaway from all this is this. All these conversion factors are nothing more than a ratio. Okay, I'm going to emphasize that quite a bit for a lot of things. We're going to use this technique down the road with respect to calculating how many grams a compound is made if we start with X amount if we start off with X amount of compound, how much of compound product we're going to make. And we're going to use this technique of using these ratios, okay? So for example, 1 kilogram could be written with kilogram, and there's 1,000 grams in 1 kilogram. I can write it with kilograms in the numerator or kilograms in the denominator, like so. Or I can just simply invert it, okay? I do that because I can use it one or the other. Which one I use depends on the question I'm asked and what units I begin with. If I start off with grams, like say 10 grams, and I want to convert to kilograms, I will use this one. Why? Guess what? My grams cancel, leaving me with kilograms here of units. If I'm given 10 kilograms and I want to convert to grams, I use this one because my kilograms cancel, leaving me with units of grams. So which ratio I use is dependent on the question being asked. And the unit that I want to get rid of will always be in the denominator, right? Because when I multiply that out, they're going to cancel out. And we're going to be keeping track of units, okay, to help us out to get to where we need to get. I will give you an example here of a very extreme example where you're given some crazy conversion factors, and it's going to go from one set of units to another set of units that you might at first glance say, well, this is crazy. How can I get from there to there? Well, you can if you have conversion factors, okay, which are nothing more than ratios. Okay, so let's say, for example, you're asked how many micrograms are in 0.125 kilograms. And I would set it up in this particular manner, okay? This technique has a name for it, and I'll be more specific here in a little bit. But basically, I would always start off with writing down what I am given. Okay, and then I end up with units of what I'm looking for. And I do that, and I take a systematic approach at this because that way I can progress with a systematic approach, stepwise. You'll get to the point where you do it so often that it just automatically at one point in time. All right, so this is where I begin, and this is where I got to go with respect to units. All right, so my first setup, obviously, I need a setup that will cancel kilograms. So I need something that cancels kilograms, and I know from the table in the previous, higher up in the page, that there are 1,000 grams in 1 kilogram. And so when I set that up with kilograms in the denominator, at this point in time, when that first conversion factor, I have units of grams, but I can't stop because I need to go to micrograms. Now, I know you might be tempted to, I need to flip this over to invert that number. I just take the inverse of 1,000. My suggestion, just leave the factors and numbers alone and just flip them up and down as you need them. Put them in numerator and denominator because it could go the wrong direction if you take the inverse here and you say 10 to the negative. What I'm saying is this 1 times 10 to the negative third kilograms per gram. You can use that factor, but it can mess up on you. So my suggestion is, unless you're 100% comfortable in doing that and keeping your units straight, then go for it. In the meantime, if you're not, I would continue with just keep my numbers whole. Don't invert anything, okay? All right. So now I insert my second conversion factor, which is given there. Let me clear this up a little bit, because you can see here the way it will set up that the units I'm given, I cancel with the first conversion factor, which gives me new units, which then I take my second conversion factor to get rid of that. And I end up with the units that I'm looking for based on the question, okay? Now the math, once I do that, the math is on you. Plug that number in your calculator. 0.125 times 1,000 times a million, and you're good to go, okay? Keeping track of your sig figs. Notice these conversion factors are exact numbers, so do not play a role. They do not play a role in determining how many sig figs you have. Remember, the exact numbers do not play a role. So we got 3 sig figs. That's what we're given. So our answer should be in 3 sig figs. Whether you write it like this or you put in scientific notation, makes no difference. Okay. You can write it longhand or write it in scientific notation. Read the question. The question may ask you to put it in scientific notation. So I need to add one more step here. if that's what's being asked. Okay. All right. So a couple other things. We give you in your shapes table 3 conversion factors. 1 inch is equal to 2.54. These conversion factors are to get us from English to metric or metric to English. Okay. And we got 1 pound is equal to 454 grams and 1 quart is equal to 946 milliliters. Of these 3 conversion factors, the bottom 2, the pounds to grams and the quarts to milliliters, are considered not exact numbers. They're measurements. That means that the 454 and 946 could be a factor in your final answer with respect to sig figs. There's 3 of them. The top one is considered to be an exact. Now it's open up to argument, but keeping in convention with the rest of the world, we'll leave it at that. And remember that 1 inch equal 2.54 centimeters is equal to 1 inch, or vice versa. It is treated as an exact number and therefore would not play a factor in your sig figs. The other 2 are not exact and could be a factor in your sig figs. The point is this: those conversion factors I can write 1 or 2 ways, as shown here. Okay. In fact, any ratio, if you're paid $50 per hour, you can write it as shown here, $50 per hour or 1 hour per $50. If you ask, okay, if I work, this one I'm sure you can figure in your head, but this is to demonstrate which one to use. Let's say, for example, you need to make $500. You need to make $500 at $58 an hour. How many hours do you need to work? Okay, so you need to make $500. Okay, and the rate that you're working is $50 per hour. So you know that you want the dollars down at the bottom, because when you multiply this out, the dollars cancel and you got the hours on top. Okay. So doing the math, obviously 50 divided by 10 says that you need to work 10 hours. That's my units left over to give me $50 to get me to $500. I'm sure you can work that in your math in your head, but that demonstrates the units. Alternatively, you can say, okay, if I work 100 hours, how much money did I make? Well, in this case, I'm going to use the conversion factor to the left because my hours are canceled. So it's 100 times 50 to give you the amount of money that you make. Okay. You can extrapolate and use speed, 100 miles per hour, same technique. No different than doing the same with all the other conversion factors, including the ones I gave you up on the top of the page. Okay. Just remember, just a bit of algebra. Remember, we're not going to do complicated algebra, very simple. Here we use letters, but you know what? If I had, if I'm doing, and those are letters in algebra, and that makes sense. But up here we're using, abbreviations. Well, no different. If I have bananas and I divide by banana, guess what? They cancel. Okay. If it's a banana orange over here, then my units that I have left over is orange. Right? All right. So when we do this, so down the road, keep track of your units. Now, with that being said, I'm going to give you an extreme example of what was trying to be shown here, how to use this method. All right. Now, many years ago, when I was teaching at Carrington, teaching chemistry, the dental hygiene students, I presented this to them and I kept it because it kind of demonstrates what I'm trying to show here. I have the question. The question is, given the following conversion factors, how many DH for dental hygiene students equal 4.5 bananas? Okay, so on the surface, you're like, this is crazy. How can you relate the two, right? That's the point. I'm trying to demonstrate how extreme you can have a problem. Because when you get the chemical reactions, you're going to be like, whoa, I'm back to DH students and bananas. But don't, okay? You can still convert from one set to another set with conversion factors. Okay, we're given that one DH student is equal to 6 grapes. Crazy, huh? 3.5 grapes is equal to an orange. Excuse the plural, but you know what I mean here, right? One orange is 6 toothbrushes, and 3 toothbrushes is equal to 1 banana. All right, so let's set up the problem. Here's the question. Those are the conversion factors. We are given 4.5 bananas, right? So I need a conversion factor to get rid of bananas. So my first conversion factor I utilize is the one I'm given, that 3 toothbrushes equals 1 banana. Okay, we're like, okay, so what that means is I got rid of my first set of units. I'm now in the units of toothbrushes if I stop the calculation at this point. But I'm not where I need to be, because where I need to be is how many DH students. So I'd look for another conversion factor that gets rid of toothbrushes. And sure enough, I got one here given to me. That I got 1 orange to 6 toothbrushes, so those cancel. My bananas continue to cancel. Okay, so at this point, with respect to units, I'm at orange. I have no concern about the numbers right now. I'm not doing any math. I was asked a question earlier. Should I do the math, one step and then round it up and do the next one, then round it up and then do the next one and round it? No, do the math completely. Because if you stop and round it to sig figs for step 1, and then do it again, next step, and do it again, you're propagating the error. So don't do any rounding until you're done with everything and you send up the problem up, and then round it up depending on your sig figs you start off with. All right, so the next step is I need one to get rid of orange, and sure enough, I have that one, or 3.5 grapes to 1 orange. All right, so still I'm not at the units that I need to be. Okay, I'm following along here. I'm just following my units. And unit-wise, I'm at grapes. So I need something to get rid of grapes. And I have, finally, I got a conversion factor where I got 1 DH student is equal to 6 grapes. Okay, check my units again, making sure that everything is canceling out with respect to units. I am finally at the units that I need to be, because that's what the question asks for. Okay, so now the math is on you. Plug in 4.5 times 3 divided by 6 times 3.5 divided by 6, whichever way you want to do it, math-wise. And then you should get this is 47.25 divided by 36. And then you end up with, after the correct sig figs are put in, 1.3 DH students. So now you can see that 4.5 bananas is equal to 1.3 DH students. Okay, very extreme example. The point to take away from this is setting up your system. This whole system, there's a name for it. Dimensional analysis is a name. Factor label method is another name to give it. I think your book uses a factor label method. I just call it keep track of your units. All right. Keep track of your units and you got the problem set up. Now, if you set it up properly, guarantee 99% that you got it up, you got it set properly. The rest is on you. That 1% is on you because you're pushing the calculator numbers. I can't control that. Okay. All right. If the question asks, and some of to show your work, and this is what they're talking about, show your conversion factors. Now, I've been asked, can I take all these conversion factors and make them into one? Sure. Okay. If you look, if you look at all of them put together here, if I just look at these conversion factors, you know, I can make one conversion factor where I got DH students divided by bananas, because everything cancels and make one unit. I can do that. But I would practice first using this technique, because when we get into equations, you know, we may have, for example, 1a plus 2b's, a general equation. A, which represents a compound, plus maybe 3b's react to give you 2c's plus 3d's. And a question may be asked, okay, if I need to make 100 grams of D, how many grams of A do I need to start? Okay. And the first thing is I find this ratio here in front, got 3B's to 3D's. So my connection is from here to here. And I got to convert them into certain units. And I would be at the minimum having at least 3 conversion factors for a typical chemical reaction calculation. And I would set that up the same way I'm doing here with respect to your units. But a lot more on that down the road. Okay. All right. So that is the example, or the extreme example of what I was trying to show you here. And what I want to do, if you have any questions before I proceed. Okay. All right. So this chapter deals with conversion of units. Okay. We're going to be going metric. We're going to go within the same unit, either English or within metric, or then we're going to get converting from English to metric or metric to English. The point being that we're going to use this ratio system to set this up. Okay. I already talked about the symbols for length and weight and volume, and given here in this table. All lowercase except volume in liters, which is uppercase L. Okay. I also showed you a PDF file with respect to the prefixes, where we got kilo, deci, centi, milli, and micro. Okay. Now I can use all these prefixes for length, the mass, or the volume. Okay. I could even use them for seconds if I needed to. Okay. So kiloseconds, deciseconds, centiseconds, etc. But normally we just keep it with meters, grams, and liters. All right, so in 1 meter, you know, there are 100 centimeters, like I spoke about earlier. We look at this question, 1 meter is equal to X number of decimeters. Well, D to me represents a decade, so therefore I got 10 decimeters in 1 meter. And then one kilometer is equal to 1,000 meters. Okay. And then we see that micro symbol, so that's a million. So 1 meter, there are 1 million micrometers. All right. And in 1 meter, there are 1,000 millimeters. So these deal with the prefixes, okay, which I gave you a table, a PDF file representing that. Now, this is the factor label method I just talked about. Like I said, you can find it in some books, call it factor label. Some books call it dimensional analysis. Dr. Fred calls it keep track of your units, okay? So we first identify the units that you're looking for. And you do that because that way you know what direction, you got to make a little trip, right? And you got to know where you're going. So you identify where you're going with respect to units, because that helps you along your little trip there to get there. Identify what you're given from the problem. You know, what is given to you unit-wise? What is the data you got to start off? And then given that, Identify the conversion factors that you need to get from point A to point B, and then setting them up properly such that they cancel out of the units that you're given to the units that you need to get to, okay? Then, of course, check it, may double check your work, and then think about your answer, okay? Really think about your answer, given the mathematics that you're doing. This is where your analysis of the math that you're doing. Because be careful, because it's a multiple choice question. Sometimes, you know, if you're supposed to multiply two big numbers, you should get a big number. But if I multiply by one number and divide it by a bigger number, I should get a number less than one. All right. And so you got to be careful. And we have some examples of what I'm trying to say here in a bit. So look at that number just because you typed it in. Don't just say, I must be correct. You know, give it some additional thought. All right, so to show your work if necessary. For example, here they're asking the question is how many liters are in 2,389 milliliters? So identify what we're looking for and identify what we're given. And so I have 238.9 milliliters. Okay. I know I need a conversion factor of some sort, and I need to get to liters. Okay. All right. Well, this may be confusing, but you know what? If this number here, this whole number is confusing, to make it a fraction like everything else, you can just put a line there and put a 1 there. Right? Same thing. That's the fractional form of a number. All right, so I got millimeters here. I need to find a factor that will have millimeters in the denominator and liters in the numerator, okay? Setting that up, I can see that milliliters cancel, and I know that in 1 liter, I have 1,000 milliliters, okay? So I set that up. Now, what if you inadvertently inverted this number and you said 1,000 liters in 1 milliliter? Think about it. 1,000 liters in 1 little milliliter, okay? Because a liter bottle, 2-liter bottle of soda pop, you know how big that is. And so if you set that up like that, like the top one, you're saying that 1,000 of these is equal 1 little tiny milliliter, 1 cc. And so that right there should be a flag thinking about, oh, wait, I set that up wrong. Also, look at the number here. You're going from milliliters to liters. So that number should be much less than the number you began with, okay? Because you're dividing by 1,000. All right. And if you were going to multiply by 1,000, heck, you're going to have even a bigger number. And that's in liters. It doesn't make sense. Think about the answer. Okay, let me clear that up. So that's what I'm given. I got my conversion factor, and I get my answer 2.389 liters. My milliliters cancel out like they should. I'm good to go. Notice that 2,000 now becomes 2.89 liters. Okay. All right, so how many kilometers are in 12,300 centimeters? By the way, don't forget your sig figs. Sig figs will never go away. We're going to use sig figs throughout the semester. So you got 4 sig figs in 2,389 milliliters. Your answer should have 4 sig figs. All right, here we're being asked how many kilometers are in 12,300 centimeters. Okay, so write down what we're given. I didn't write it down here, but I normally would write down the units that I'm striving to obtain, kilometers, and that's what's showing me the direction to make sure I set this up properly. All right, so my first factor is in centimeters. I need to get rid of centimeters. And I know from my tables that in 1 centimeter, in 1 meter, there's 100 centimeters. Okay. That allows me to cancel my centimeters, which leaves me with the meters. Now, I know that 1 kilometer is equal to 1,000 meters. And so now I can set this my final factor and leaving me with units of kilometers, which is where I need to be. And now simply you multiply and divide. Okay. Again, you're dividing by some big numbers here, some numbers. So your number should be 0.123. Now, I've been asked the question, can I combine these conversion factors? Of course, yes, you can. Okay. These two here, yeah, I can combine those. Oh, no, 1 second. You take 1,000 and 100, multiply it, right? And what should you get? You should get, what do you get? 100?
100,000.
100,000. So I can convert, I can make 1 unit here. Oh, I'll put my pen back. I've been having trouble with my mouse. So I can combine these and say that I have 1 kilometer is equal to 100,000 centimeters, right? Because see, I can see how these cancel. I can make 1. And if you see that, you're go ahead and use that, okay? But I recommend keeping separate until you're comfortable with that. Now, because remember, eventually when we get to the chemical calculations, you're going to have at least at the minimum for some of these chemical calculations, at least 3 conversion factors. Okay. All right. The English units, I know we got 2 cups, 1 pint, 2 pints, et cetera, standard 2 inches a foot. These are factors that we utilize. If you know more of other ones, feel free to use them, whatever conversion factors you're comfortable with. For example, I'm more comfortable with 5,280 feet per mile, but that's equal to 1,760 yards per mile. Yeah. So whichever you're comfortable with. But those are the English units. The volume ones always got a hold of me. I kept, well, how many cups in a pint? I always forget. So I use this to help me out. The G is the gallon. Okay, 1 gallon. And inside the gallon, there are 4 Qs, which represent 4 quarts. And each Q are 2 Ps, which represent 2 pints. That tells me there's 2 pints per quart. And inside each pint, there are 2 Cs that represent cups. So there are 2 cups per pint, okay? 2 pints per quart, 4 quarts per gallon. Each one of these is a conversion factor. Every one of these is a conversion factor. I can write 2 cups per pint or 1 pint per cup as a ratio, okay? So I got 1, 2, 3, 4, 5, 6, 7, 8, 9 conversion factors. I got 18 ratios so that I can write these up. And which one you need depends on the question. Okay. For example, we're going to stay within the metric units. They're asking you here, how many gallons is 4.5 cups? All right, so we write down what we're given, right? 4.5 cups. I am need to go to gallons. Okay, keeping track of that, so I know which way I need to go. I know that from this little image here that there's 1 pint in a cup. Okay. So you can see I set that up with cups in the denominator because when I multiply it by that factor, my cups will cancel, which leaves me with pints. So I need a factor now to get rid of pints and put me into a different unit, which in this case is quarts, because I know that 1 quart is equal to 2 pints. And then finally, a final conversion factor, which is 1 gallon is equal to 4 quarts. Yes, granted, I can combine all these. You know, how many cups in a gallon? Can anybody tell me?
16.
You got it. Because I can make a new factor. 1 gallon is 16 cups, right? Because I just multiply 4 times 2 times 2, my pints cancel. All right, but until such time that you're more comfortable, use each one. You know, so my cups cancel here, leaving me with pints, and my next conversion factor gets rid of my pints. My final conversion factor gets rid of my quarts. I'm now in the units of gallons, which is what the question asked for. All of these conversion factors are exact numbers, and therefore we're not playing a factor with respect to conversion factor, sig figs. So my answer should have 3 sig figs. Okay. 2.78 gallons. All right, and we got another one here. How many inches in 3.5 yards? Write down what we're given, 3.5. I don't have the inches written here, but that's okay. I do know there's 3 feet to a yard. Okay. That will get rid of my yards and put me in feet. Obviously, there's 12 inches to the foot, excuse me. Okay. And then there are finally 126 inches. Now, quick question, let's double check. All right, my yards cancel, my feet cancel, leaving me with inches. I'm good. Would I present my data as 126?
Would you round it up to 130?
You got it, right? And why is that? Because look at my sig figs here. I got 3.2 sig figs. 2 significant digits. So my answer should have 2 sig figs because I'm multiplying, right? Now, these conversion factors are exact numbers, so they don't play a role in determining sig figs. So my answer needs to be with 2 sig figs. That means I find my 2 sig fig position, which is the 2. And like we've been doing, I look at the neighbor. Okay, the neighbor is greater than 5, so that 2 becomes 3. Now, don't drop that 6, right? You convert that 6 to a 0. Remember, the magnitude here, you're in the 100. The magnitude is 100. And if I were to drop that 6 completely, I'm to 13, you know? So you're at the 100 range. That's the magnitude. I mean, which would you rather have? $100 or $13, you know? So yes, you will round it up and change the 6 to a 0. So any numbers that get removed before the decimal point get converted to 0. Any numbers after the decimal point you can drop because you don't change the magnitude. And if you went this way and did this, what have you done? You have created significant digits. You have created 4 sig figs, but your measurement is only accurate to 2 sig figs. So it will be incorrect to add more accuracy when your digits you began with are not that accurate. Okay. I hope that concept makes sense because I think a lot of times our educational system, as you progress, and I was guilty of it myself, I used to think, hey, I'm going to put it 126 inches there. It's more accurate, but you can't be more accurate than the tools you had to measure with. Okay. Can't put it more accurate. Okay, so 130 inches would be the answer with the correct significant digits. As I mentioned earlier, these conversion factors, which you find on the shapes table, okay? One of them is exact, it's treated as an exact number and therefore wouldn't play a factor determining sig figs, but the other two are measurements that are approximate and therefore could play a factor. Now, yes, there are like a variety of hundreds of conversion factors. In other words, if you Google how many grams in the pound, you will get a variety of answers. You will get 454 point blah, 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 blah. Our recommendation is to use these conversion factors and not what you Google, because these conversion factors, if you use them to do any calculation, the answers in Canvas are based on the digits of these calculators. In fact, to give the correct number of sig figs. Canvas is not AI and doesn't know any better. Okay, so use our digits and to determine, if necessary, the correct number of sig figs. All right, some more examples. And we got here, how many pounds are in 248 grams? Well, here's the conversion factor of metric to English, and that 1 pound is 454 grams. Okay, I set it up with grams in the denominator, the 454, because I want my grams to cancel out. And so, okay, leaving me with units of pounds because that's what the question asked for. I got 3 sig figs in this calculator, remember, and this conversion factor, remember, this is an approximate, it's a measurement, but I got 3 sig figs in the number that I'm given. Therefore, our answer should have no more than 3 sig figs, okay? This one's a little bit maybe more. 3.54 times 10 to the negative third kilometers, okay? And so we have the first factor where we're getting rid of kilometers. My first factor gets rid of kilometers. Okay. And then my second factor gets rid of meters and puts me into centimeters, because my conversion factor to get me into inches, this is what I'm looking for, is 1 inch is equal to 2.54. Okay, so I first converted the kilometers to meters, and then from meters I went to centimeters. Can I go direct? Yes, I can, but combine these two. But until you're comfortable with it, keep them separate. And then my final one converts those centimeters into inches in my answer. Okay. All 3 conversion factors are exact, so would not play a factor in sig figs. We have 3 sig figs in what I'm given, 3.54. And then just plug the numbers in and there you go. Then we got 2 liter soda bottle contains how many quarts? So we're converting liters to quarts. So we convert liters to milliliters first, because why? I have a conversion factor that goes from milliliters to quarts. So if I can convert my liters here to milliliters, then I can go into quarts, right? So I use this to give me into milliliters, and then finally milliliters into quarts. All right. Now, if the problem you're asked is to show your work, then this is what we're talking about, using these conversion factors. But if it doesn't say show your work, you can combine all your conversion factors into one to get your answer, okay? All right. Work on your exams and so forth, because the worksheets are there to help you out. I did send you an email concerning well, I think it was Dr. Dana and Dr. Kim that are offering sessions. And even though they're GCC students, you're more than welcome to go to the sessions and they go over these type of problems. Also, I mentioned before, and I'll state again, I'm teaching Tuesday and Thursday, 1 o'clock and 4:15. You guys are more than welcome to attend those sessions, to get more of the same. Yeah, so a lot of resources. All right, any questions right now with respect to any of these type of conversion factors? Okay. Yeah, go ahead.
I just have one question. When you rounded up with the last example, why didn't we round up with the one that we just did on number 2?
This one here.
Yeah, we
Okay.
rounded up on the previous examples you gave us, but why didn't we round up for that one?
Okay, in the well, like that one, right?
Yes.
Because we're keeping track all along. We also keep track of your starting number of sig figs. Let's take the first one here. How many sig figs in 44.5?
3.
Okay, we got 3 sig figs. Now, all these conversion factors are exact. So they will not be a factor in determining significant digits. Therefore, when you do the math, your answer should only have 3 sig figs. Okay? All right. How about the second one? How many sig figs here?
2.
Exactly. And then again, all these are exact. All right. So when you do the math here, your answer comes out at 126. How many sig figs here?
3. I see. So we round up because that 0 at the end of 130 doesn't count as a significant figure.
You got it.
Thank you.
Yeah. Good question. There was another question there?
Yeah, so as far as like these recordings for this video, because I missed some stuff earlier into the video, how do I access like after like class and stuff?
Let me I can actually, but if you go to the course website, on the far left panel, there should be a button there. You click it and it opens up a tab to the site that I've uploaded all the files. Let me see if I pull that up here real quick.
And it'll in those videos, it'll show you doing the work and stuff like that also, just so I can refer back to.
Yeah. Everything that's going on here, it will show you. Let me get to that, your course. Come on. All right, now let me share your course, the student view. And I'm assuming, because my screen looks a little bit different, but your course should look something like this. You see it?
Yes.
Everybody see it? Now, if you look at the far left, here's the Zoom button, but down here you got the recordings. And if you click that, it's going to ask you if you want to open to a new window. Make sure I'm at that window. Yeah. And you should see all the recordings here. Now I label them, I got GCC here and I label them the times and all that, but I also got SCC. So, and I show what it is. So you're more than welcome to go and listen to any of those. Also in your modules, every chapter Okay. Can you guys see chapter 1 module?
Yes.
There's videos in there. Those are pre-recorded videos by Dr. Kim, a different instructor, of this topic that we're talking about now. Okay. And so not only do you have access to this information beforehand, you have access to the recorded videos that we talk about here. Okay. All right. Does that answer your question?
Yes. And then how are they usually uploaded also like after the class, or is
Yeah.
it like later on in the day?
Well, what happens is it takes a little time because after I'm done, I need it. Zoom converts its format into an MP4, and since we're talking from 1 o'clock to 3:40, our files tend to be a little bit bigger, and so it takes about a good some days 30 minutes, some days 15. I don't know. It depends. And it depends on the phase of the moon. I don't know. But eventually, when Zoom's done, I upload it, and then YouTube has to put it in its format, and it does its checks. And so I try to get it uploaded within an hour or 2 hours after we're done.
Okay, thank you.
Yeah. And what some students have done, they subscribe to that channel. So every time something gets uploaded, you get notified when it's ready to roll. So you might try that. Okay. All right. Any other questions? Uh-oh. All right. So these are the conversion factors. So, and I realize you can combine a lot of these conversion factors, and that's good. But I recommend you do it the long way with all the conversion factors, because again, we're going to rely on this factor label method, dimensional analysis method, whatever you want to call it, when we get to the part where we're doing calculations for chemical reactions. Okay. All right. Any other questions? Okay. Well, I tell you what, let's take maybe a 10-minute break. Okay, let's come back at 2:29. I call it 2:30. All right, take a little short break. Let me pause. Okay, guys, I'm back. Let me stop here. Okay, let's finish up this chapter here. We were finishing up here. Okay, so any other questions concerning these conversions? I'm trying to close some files here because my system is kind of slowing down. Bear with me. Okay, so we're going to talk about I introduced density a while back, but we'll kind of bring it back a little bit here because we're going to talk about doing calculations with respect to density. Okay, but first we're going to mention about the volume. Now, like I said, it's related to density. To refresh your memory, density is simply another ratio, which is mass over volume. Okay. Now, if you have a substance that's, regular shape, like a rectangle box, we can measure its volume very simply by, length, width, and height. We're good to go. Take its mass. Boom, we got the mass, we got the volume. Okay, we're great. However, not everything is that straightforward. There's items out there that have irregular shape, and it's difficult to get a direct measurement. So what we do is we measure its volume by displacement, by the displacement of liquid in which we put it into a container. No different when you jump in the tub, you jump in the jacuzzi, whatever the case may be, swimming pool. Your volume, your mass pushes that liquid up, that volume up. And so if you have a means to measure the volume to begin with, you jump in, volume goes up, you're completely immersed. Somehow you get that measurement of afterwards. That difference is the volume that you displace. Okay. And so refresh your memory, 1 milliliter is equal to 1 cc. Most of the time, the density is given in units of milliliters, but be aware it could be cubic centimeters or it could be written as cc. So we got a diamond, for example, and you can pick up the diamond. It could be anything. We put it in a graduated cylinder, which is a cylinder with a scale on it so we can measure volume. And it starts off with 20 milliliters of water. So we put the diamond in there, and guess what? The volume goes up as expected, okay? And it goes up to a new volume of 34.7. The question is, what is the volume of the diamond? The volume of the diamond is the difference of the volume that you measured minus the volume that it was to begin with, okay? That volume of that diamond is not 34.7 milliliters. That's the total volume. That's the total volume of the 20 milliliters plus the volume, excuse me, of the diamond. And so the volume of that diamond is only 14.7 milliliters. Okay, it ended up at 34.7 minus the 20 milliliters that it began. So the volume of that diamond is 14.7. Now you can measure its mass. Divide the mass by the volume, you have the density of that particular diamond. Okay. All right. So how do we calculate? As I mentioned, a rectangular box, we simply do a measurement, length, width, and height. We got a box here, 24 centimeters by 11 centimeters by 16 centimeters. Okay. It's 24 times 11 times 16 gives you 4,200. Okay. Hold down. Give me 1 second, please. Okay, I'm back. Sorry. So 24 times 11 times 16 gives you 4,200. Obviously, centimeters times centimeters gives you centimeter square, times centimeter gives you centimeters cube, or cubic centimeters, or 1 milliliter, right? Or milliliters. All right, density. As refresh memory, it's a ratio, mass over volume. Okay. And so those are the units of density, which could be grams over cubic centimeters or grams over cc's, but the unit that is used most often is grams per milliliters. Okay, think of density as how much matter is in a given space. So it is. We know that, based on the measurement, based on the property of solids, solids are the most dense material that we have. And the least dense will be the gases, okay? And an example would be like a density of air in the order of 0.00129 grams per cubic centimeter. Density of water is at room temperature is 1 gram per cubic centimeter. And you can see gold or most any metal, anything Heavy has a density much greater than 1. As a general guideline, what we do is we use our reference point of the density of water as 1. That's our reference point. So anything with a greater density, greater than 1, tends to sink if put in water, okay? Or anything less than 1 tends to float. All right, so how do we do these density calculations? Well, type 1, straightforward. Simply divide the mass that you're given by the volume that you're given. All right. Type 2 density type of calculations, we're going to be given a density of a chemical, a compound, and from that we're going to calculate either the mass or the volume. Keep in mind that that density is, again, simply a ratio. So for example, the density of chloroform, which is an old chemical used to use to knock people out when you had an operation, knocks you out. It has a density of 1.48 grams per milliliter. Okay, think about it. 1 milliliter, if you take 1 milliliter of chloroform and weigh it, it will have a mass of 1.48 grams. Okay. All right. And as any ratio, just like the conversion factors that we utilize, I can write it one of 2 ways, with grams in the numerator or grams in the denominator. Which one I utilize to do my calculations depends on the problem. Okay. For example, let's do a straightforward one. What is the density of a necklace that is 484.56 grams, has a volume of 25.64 milliliters? Simply put, you set it up, mass over volume, plug in the numbers, okay, and do the math. Keep track of your sig figs. Numerator has 5 sig figs. Denominator has 4 sig figs. Our answer should have 4 sig figs, okay? Because the denominator is the least accurate digit. All right, some other problems. Let's say, for example, we have the density of chloroform, same chemical we talked about earlier. It has a density of 1.48 grams per milliliter. The question is here, how many grams would 17.5 milliliters of chloroform mass? Okay, now we do the process like we normally do. We write down what we're given. 17.5 milliliters of chloroform, okay? We know we're going to have a conversion factor here. And what are we looking for? Unit-wise, we're looking for grams. So I want to set up my conversion factor here with grams in the numerator and milliliters in the denominator, right? Because I want milliliters to cancel out. And so now I got my unit set up properly. I just put in the numbers now, okay? And once I do that, I simply do the math. And let me clear it. Okay. And it becomes, my answer is 29.5. Again, keeping track of your sig figs. Now, density is a measurement. So it's not an exact number. So density is a measurement. So it could be a factor with respect to significant digits in your answer. All right, so 1.48 has 3 sig figs. 17.5 has 3 sig figs. So your answer can have no more than 3 sig figs. Okay. Also, which I see a lot, I don't quite understand, but I see it a lot. The answer is presented as grams per milliliter. Well, that can't be. Okay, think about it. You're looking for grams. Okay, and you know the way this is set up that milliliters cancel out. So there cannot be in the final units milliliters. So it's a matter, again, looking at how you set that problem up. Okay. All right, now let's do the other type. They're asking you, how many milliliters would 0.035 grams of chloroform occupy? Okay, so like we done before, we write down what we're given, grams of chloroform. Obviously, we're going to have a conversion factor here, and we're looking for units of milliliters. All right, so we want grams in the denominator and milliliters in the numerator. Grams cancel, and now I simply put in the numbers. Okay. And then simply do the math in your calculator. Okay, grams cancel. And so I have 3 sig figs in both numbers. So my answer should have no more than 3 sig figs. So 0.0495 milliliters. Okay, not milliliters per gram, just simply milliliters because the grams cancel. And so 0.735 grams, if I put that into a cylinder and measure its volume, we have a volume of 0.0495. Okay. All right. So you have 3 ways to do density, 3 types of density calculations. One, the straightforward mass over volume, and the other 2 is you either calculate grams from the density or you calculate the volume from the density. Okay. Okay, let's move on. Which brings us to a little bit about this temperature and energy, which, I think it's pretty self-explanatory. I'm not telling you anything here, no rocket science. I think you already know what's going on here. Hot molecules, they move fast. I mean, they move very fast because they have high energy. You can feel, get a pot of hot water boiling, put your hand over it. You can feel that vapor, being pushed up against your hand. A steam engine, that's what a steam engine works, that hot water molecules, because they move fast because they have high energy. And obviously the converse of that is cold molecules tend to move slow because their energy is much lower. Okay. Now, temperature is a measurement, and we use obviously a thermometer. Okay. Temperature is not an energy, it's just a measurement. The energy into the system or taken out of the system affects the temperature. You know the difference? Okay. So it affects the temperature. And we use 3 scales. We're familiar with the first one, Fahrenheit, because we still use the Fahrenheit scale. And then we have the centigrade, the Celsius, and then we have a new one you may not be familiar with. We call that Kelvin, named after Lord Kelvin, another British scientist. Now, the thing about the first 2 scales, these scales go to infinity, in the positive direction and in the negative direction, both the Fahrenheit and the centigrade. The Kelvin does not. Kelvin stops at 0, someplace down here. This is absolute 0. Okay, this is what has been proposed, that all matter stops movement completely. Even as you get down to cold to temperatures, the molecules themselves are vibrating in the solid phase, so they're still moving. But when you get to that position, even that's supposed to stop. We've not reached that position, came close, but not close enough yet. And the other aspect about that down in this area, there's some very interesting phenomena that's occurring. It's obviously being worked on and studied further. Okay, so we got 3 scales: Fahrenheit, Celsius, and Kelvin. Okay, now Celsius and Kelvin are related to each other by a factor of 273. Meaning, if I want to get from Celsius to Kelvin, I simply add 273 to my Celsius value. Okay. Fahrenheit, there's no connection, direct connection from Fahrenheit to Kelvin. If I start at Fahrenheit, I gotta go to Celsius first to get me to Kelvin. If I start at Kelvin and I want to go to Fahrenheit, from Kelvin, I go to Celsius first, and then I convert to Fahrenheit with respect to the temperature. Okay, and the equations for that is there. Now, you don't have to memorize them because guess what? They're in the shapes table too. But very straightforward is the first equation. If you are in Fahrenheit and you need to go to Celsius, you simply subtract 32 and then you divide by 1.8. If you are in Celsius and you want to go to Fahrenheit, multiply your Celsius by 1.8 and then add 32. Okay. And then for Kelvin, just you need Celsius and just simply add 273. So with that, try 115 Fahrenheit, convert that to Celsius and Kelvin, and you should come up with 46 Celsius and 319 Kelvin. Try that, see if you come up with those answers. All right, with respect to heat / energy, you can see there's two beakers here. You know, they ask you the first question, and you're like, oh, wait a minute, sounds like a great question. It says, which of these two beakers has a higher temperature? Well, they both have the same temperature. I'm assuming that red line's a thermometer and is registering at 100 degrees Fahrenheit. Okay, so they're both at the same temperature. And then the second question is, which has the greater amount of heat? Well, think about it. The first one, A, has a higher volume, there's more matter. And the second one has less, B has less material, less liquid. And so just the fact that there's more matter, A, should tell you that has a greater amount of heat. An analogy to that would be like, okay, I got a big old pot of on the stove boiling so I can make spaghetti. And then right next to us, I got a little small pot of water boiling to make a little cup of tea or something. All right. And then ask yourself, okay, if these were going to be spilled on me, which one would I want? I have a choice. Select one or the other, the big pot of water or the little pot of water. Well, obviously the little pot. Yes, they're both boiling at 100 degrees Celsius. They're both boiling, but the little pot has less matter. So the damage, the pain will be a little bit less than that big old pot of water. That will be quite the problem. Okay. All right. So heat transfer. Now, Mother Nature always goes from high energy level to low energy level. Okay. Spontaneously. All right. You can go up the other direction, but not spontaneously. You got to put energy into the system. That's how your air conditioner works. You know, it's not spontaneously becoming cold. You are putting energy into the system to bring that temperature down. But you do know if I make a cup of coffee or a bowl of tea or a bowl of soup boiling nice and hot, and you leave it on your kitchen counter and you come back an hour from now, what's happened to that temperature? It has dropped because that hot temperature is high energy, and Mother Nature being Mother Nature doesn't like that high energy state. It goes down to the ground state. So eventually that bowl of hot material equates to whatever temperature the room is. Okay. And so here heat transfers from high temperature to low. Okay. And heat transfers from hot to cold. So if you take a cookie straight out of the oven, who's going to lose the heat? Obviously the cookie, right? High energy. And who gains the heat? Your hand. And if it's real hot, you're going to feel it. So your hand gains the energy and the cookie loses. Eventually they're going to equate, right? In this example here, you got a piece of metal that's placed in a freezer and you put it into a hot bucket of water. The question is, does the temperature of the metal increase, decrease, or stay the same? What do you think would be the answer? Boiling, hot, you got a piece of metal in the freezer and you stick it in the hot water. What's happening to the temperature of the metal? What do you guys think? Would that metal increase temperature-wise, or would it stay the same? No takers? Okay. It will increase. Thank you. Of course, right?
Increase, yeah.
Yeah, it makes sense because again, the hot water is a high temperature, high energy, and the metal is the low energy. So the heat transfers from there. Okay. And does the temperature of the water in the bucket increase or decrease? Well, as the hot water transfers that energy itself, will reduce its energy level, so its temperature drops. Eventually, both of them will equilibrate to whatever temperature it is around its environment. If it's in your room, then it's all going to end up at, say, 25 degrees Celsius, room temperature ballpark. All right, so coming soon, coming soon. Next Wednesday, you got the exam, do the worksheet. Again, you have 2 sets of YouTube videos, one done by Dr. Kim concerning this topic, pre-made already. So you're more than welcome, obviously, to go read that, listen to it, I should say, and then we have the ones we record here. Okay, so do work the problems, practice conversion, the density and temperature problems with respect to converting temperature. Sig figs, we use sig figs all the way to the end of semester. So we're done with it here. It doesn't end. Okay. All right. That being said, we are done with chapter 3. Does anybody have any questions concerning chapters 1 through 3?
I had a question about the time on the due dates. So are all the assignments always due at 11, or does it change to like 11:59?
All the assignments, they're at the ones that are due, they're either going to be 10 or 11.
Awesome. Thank you.
Okay. 10 or 11. So, yeah, check it when you start it. It'll tell you there which one it is.
I had a quick question about one of the examples.
Sure.
I think on one of them you put grams over milliliters after the answer, and I was wondering because you said that like because normally the milliliter would cancel out during the
Yes.
math process. So I was just confused on how it was the first example when we went
Oh,
to
okay.
I forgot. It was the one that was 484.56 grams over the. I don't know if you can find it.
This one right here,
I think it was back.
or
Yeah. Yeah, that one. Because in the answer you put grams over milliliters, so I was kind of wondering like.
okay. Well, for this type, this is a straightforward. They give you the grams, okay? They give you the grams, and they give you the volume. So it's a straightforward plug in the numbers. Plug in the numbers into the equation, like shown here, with their units, and then it stays, these are, they don't cancel out. So that is, by definition, that is the density of this particular necklace.
Oh,
Okay,
so that's what you were saying, that it depends how you set it up.
right.
Because if we were to
Now-
set it up the other way, the milliliters would cancel out and you would just have grams.
Like for
Okay.
example, yeah. Let me give you, I think I know where, like right here. So here the problem says, what is, how many grams would be 17.5 milliliters of chloroform? So we write down what we're given, okay? And then you write down the density, set up with milliliters in the denominator. You see how why it's set up like that with respect just to the units, because they cancel out, the milliliters cancel out, right? And notice here, the question says how many grams? So your answer should only have units of grams. But what happens occasionally, students tend to forget that the units cancel. And what they do is they carry over the units of milliliters. That would be incorrect. Because first of all, grams or milliliters is density, okay? And the milliliters here cancel right here. So you should only have one unit, just grams. And the other problem where you're looking for grams, and this one you're looking for milliliters, here's the situation here. Same thing. You should only have one set of units because the question says how many milliliters. It didn't say how many milliliters per gram, just how many milliliters. So your answer should only have one. And sometimes, occasionally, for whatever reason, students would add the grams to it. Again, same thing as up here. That would be, incorrect. Okay. Is this where I was talking about that kind of confused you?
I think it was just like the words and the word problem because I don't think that first one asked for grams or milliliters, but these two do. So
Right.
I was kind of confused, but yeah, I get it now. Like you really have to read the word problem too.
Yeah, exactly. And that's a paying attention to detail with respect to the questions is crucial. Not only here, but it is a skill set with respect to getting out in your job in your industry. Very, very important. Paying details very, very important. Okay, yeah. Any other questions?
I actually have a question.
Sure.
So exam days, it was for chapter 1 homework. Which day of the week does it fall on usually?
Say that again. I'm sorry, you broke up.
Exam days, which day of the week does it usually fall on?
Oh, I try. Exam days where the first one I had to fluctuate a little bit because it's pretty. We got 3 chapters, a lot of information, so on and so forth. So I moved it to Wednesday. It's coming Wednesday, but normally now things are going to kind of smooth out a little bit. We're going to have ballpark. We're going to have a little more time and not be so rushed. Or the exam days will be. I try to make them on Saturday. Okay.
Yeah.
If those days don't work out for you, I can adjust maybe 2 days forward, 2 days back.
That's what I figured, but it actually wasn't an option for the question. It wasn't a choice to be selected. So.
Well, I don't follow the question. It was a homework question?
On Canvas, it was chapter 1 and it had almost every day except for Saturday.
Oh, okay. Okay. Unfortunately, I didn't update that. Let me know which question number that was, and I will go in there and I'll check everybody's answer and give credit for that question.
Awesome. Thank you so much.
Okay. But shoot me an email to remind me, okay?
Okay, right. I will.
All right. Okay. Any other questions?
Oh, for the lab for this week, are you gonna go back and grade the typed answers that we typed in?
Yeah, that's my weekend assignment.
Right.
Yeah, so I wait till everybody's done and I spend some time this weekend answering them. Yeah, it should be done by Monday for sure. Okay. Any other questions? Okay. Well, what I'm going to do then is I'm going to go ahead and jump in question number, excuse me, chapter number 4. Okay. If you have any questions between now and Wednesday, feel free to shoot me an email, and I definitely will keep an eye out for it. And especially on Wednesday on exam day, I'm very diligent about keeping close to my computer and keeping an eye out for questions. Okay, so I'm gonna try to get back to you as soon as possible. All right, so this brings us to chapter 4, which we're gonna talk about atoms. Okay, now we're getting back into chemistry. And we have to introduce a little bit of mathematics. Not too bad. All right, so this model that we have really got to start, this quote modern model, got to start back in the 1800s. Scientist by last name Dalton had what he called the atomic theory. He proposed that an element was made up of tiny indestructible atoms, which he called atoms. Okay. Well, that's not quite 100% as far as being indestructible, because we learned since then that these atoms are made up of subatomic particles. And we're going to talk about those. The 3 main ones are protons, neutrons, and electrons. And then guess what? Those guys are even made up of even smaller particles. But we're going to stick with protons, neutrons, and electrons. He also proposed that all atoms, the concept of an atom is not new. The Greeks had a same concept, and the concept of elements is not new either, because the Greeks also had elements. They only had 4 though. We got 118, but they had earth, wind, fire, and water were the elements according to the Greeks. Earth, wind, and fire. Good bang. No. So he proposed that all the elements were identical, which is a true statement, and all they have the same properties, which is not a true statement. We learned that, for example, carbon can exist as diamonds, one of the hardest components on Earth, material, or it can exist as a graphite material, very powdery, slimy material. In both cases, they're carbon. But because the way they're put together structurally and relative to each other, they have totally different properties. Okay. Also, we define, as I mentioned earlier, that a compound is made up of 2 or more different elements. In this example here, we got, looks like 2 diatomic elements coming together to form a compound. 2 different elements combined. Okay. Part of his theory. We also had part of his theory was that compounds, when combined, when the elements, I should say, combine to make compounds, they combine with whole numbers. So we won't find like half an atom or a 3/4 atom or partial atom. They're going to be whole numbers. And so when we write a formula like H2O, okay, H2O, that tells us that we have 2 whole atoms of hydrogen and 1 hydrogen. Now, 99% of those formulas that we write out, we write the first element that we write down are what we call the central atom. In other words, if I were to write carbon dioxide, which the formula would be as follows: carbon is the central atom, and then the 2 oxygens that follow are bonded around the central atom. And that's like 99% of the time we're writing the formula. The only exception is H2O. By convention, they write the 2 hydrogens together and then the oxygen. But in reality, we've now learned that oxygen is the central atom. And when I draw a line like that, connected to a hydrogen, that line represents a bond between the oxygen atom and the hydrogen atom. Okay, that's what that line represents. We're going to learn that line represents 2 electrons, but more on that later on. Okay. Now, also atoms can, of 2 different elements can combine to make 2 different compounds. A classic example is carbon monoxide, okay, which has the following right here, carbon monoxide and carbon dioxide. So here, carbon is represented, let me change the color here. Yellow, that's carbon, and here's the oxygen, okay? That's carbon monoxide. Here we got carbon again, and then bonded next to it are the oxygens, okay? And so totally different species. Yeah, carbon monoxide, poisonous gas. Carbon dioxide, important gas for plants, right? But there's still carbon and oxygen, just in different ratios, whole numbers again. Notice the naming, okay? Carbon monoxide, mono meaning 1, carbon dioxide, di meaning 2 oxygens, dioxide, okay? It's just a precursor to nomenclature or naming these compounds. All right, so that was the model that we had so far at the point, you know, he just didn't know too much about it. Dalton, that is, but that was what he's proposing. Now, 1897. All right, this is the beginning here. We're going to get close to the beginning of the 1900s, because during this time period, all kinds of scientists were coming up with some new discoveries. It's just like we just got boom. This is a time that Einstein's around, but he's not alone. There's other scientists that are just as bright as Einstein, but Einstein's got the better rep, I should say. All right, so here's a guy called J.J. Thomson. He is credited with discovering the electron all the way back to 1897. Unbeknownst to him, he is also credited to creating the precursor to the old-fashioned televisions that we used to have, you know, the big heavy ones. He used to have one myself not too long ago, so I got rid of it for my flat screen. But the old-fashioned television sets. Now, the way he did this is that he had this piece of equipment that created this particle beam, okay, called cathode rays. That part's not important. It created tiny particles, okay? And the way he set it up, he was able to direct that particle onto the screen that contained some material. Now, as I stated earlier, energy goes from high to low. Well, these particle beams are pretty high energy. And when they collide with the surface of the screen, the molecules on that screen absorb that energy and get kicked up to a high energy state. Nature being nature, molecules don't like to hang out there in a high energy state to come back down. And when they come back down, conservation of energy, what energy goes in must be released as it comes back down to the ground, what we call the ground state. When it did that, it emits some of the energy as light. So he was actually able to see that screen, okay? And then he found some other information. I'm going to stop it in between in their conversation here. Okay, let's talk about it. Notice here on the screen that particle travels and hits the screen, emitting light on this side, okay? And like I said, this is the precursor from the old-fashioned television. So you're sitting over here, the old days, watching cartoons, okay? The old-fashioned TV, but obviously they didn't have the TV at 1800s. But this was the beginning of it. And now he places a current through here. Notice the current is negative. You get the negative side there. There's a negative, and it's causing that beam to be deflected. See how the beam deflects down? Okay. And so that tells JJ here that that beam must have a charge because, and it has to have an opposite charge of what's being displaced here because opposites repel each other. And it's coming toward the positive side. And so that told JJ Thompson here, that beam is a negative charge particle. So any charged particle has associated with it that's traveling, has associated with it a magnetic component. And so this charged particle with a negative charge has a magnetic component. So if you bring a magnet to it, it will deflect that beam. And that's why those old-fashioned televisions were so heavy, because in the back of the screen were 4 giant heavy magnets that controlled that beam to go in whatever direction they needed to go. It actually scanned back and forth. Okay, so this is no different than a motor, electric motor, or a power, something that creates electricity, generator. Because we can play with the current passing through, we can play with the magnetic component to either create an electric motor or to create energy. Okay, electrical energy. Okay, give me 1 second. Okay, obviously this equation we're not going to get into at all. But the point about this equation was that he had this ratio and he had this constant on the right side of the equal equation. And that allowed him, once we knew the charge, what E was, to calculate the mass of this electron. And it turns out that it's extremely, extremely small. In fact, the electron is so small, we basically don't give it a mass at all. Okay, we give it a mass of 0. More on that later on. Okay, so what he comes up with is his particular model of how the atom is put together. He says that he basically amounts to what's called the plum pudding model. The electrons are somewhere in this atom. We don't know much about it. And there's maybe a positive component in the center someplace. So that was a model. Before we didn't even have that, but we got a model so far up to this time. 1904, okay? Here comes another scientist, 1911, Rutherford, also a British scientist. he kind of took some of the ideas of JJ, but he kind of changed it around a little bit. What he did, he also created a particle, specifically alpha particles, but we're not concerned about that. And he shot these particles through a layer of gold, okay? A thin layer of gold. And he also had the screen around his equipment. Now, if the plum pudding model was correct, he thought that then these particles will go straight through. You'll see the image on the other side of the screen, and that was it. What he found, however, that some of these particles were being ricocheted. Okay, they were being angled off like shooting pool. You're trying to get the ball to the corner pocket. It went at an angle. Some of them was shot back to the source. And so what that meant was that particle, which is pretty small, must have hit something that was pretty dense, enough for it to ricochet at a different angle. So what he is credited, that is Rutherford, he is credited to discovery of the nucleus, that there's a nucleus / proton, okay? Okay, so on the far left, it was Thompson's model, the plum pudding. And if that was the model of what these atoms and all the subatomic particles, how they're all put together, then all of the particles would have shot through, and that would have been the end of it. But the fact that Rutherford found that they were not, they were being ricocheted, the particles that is, he concluded that in the center of the atom must be a very dense area, which is the nucleus. We find out that that is where the proton, we determine that that's where the proton exists, and that is where another subatomic particle called a neutron exists, with the electrons somewhere on the outside. It's proposed they're very similar to the solar system at the time, but we're going to learn that these electrons around the atoms actually exist in very specific energy levels, okay? And so 1917 is the proton for Rutherford. It wasn't until the 30s and 1932 that the neutron was actually discovered, and that was by James Chadwick, okay? So our model at the time, very similar to that diagram, where we have the nucleus, which consists of the proton and the neutron, and then the electrons are orbiting around the nucleus, okay? But we also learned that the atom is mostly an empty space, and very empty space. In fact, if I were the hydrogen atom nucleus, I scaled everything up to my size, and I'm represent the nucleus, my electron will probably be about 3/4 of a mile away from me. That's how far away. So there's a lot of empty space in between. A lot of energy involved too in this interaction between the electron and the proton. You know, hence the hydrogen bomb, atomic bombs. There's a lot of energy there, splitting of the atom. Another analogy to give a size of these atoms, to give a perspective, is if the nucleus again was the size of a marble, then the Cardinal Stadium would be the size of an atom. Okay, so a lot of empty space. So the subatomic particles that we're going to talk about And bear in mind, keep in mind that these guys are made up of even smaller. We're not going that there. So there's the electron, the proton, and the neutron. The symbol for the electron is the letter E, lowercase e, with a superscript negative, because it has a negative charge. Its location is outside the nucleus, okay? Its mass is relative mass, what we call AMU, atomic mass unit. What they do is they give it a relative mass. Now, how's that work? I'll give an example. Let's say I'm at 200 pounds. Somebody else is at 400 pounds. So our relative mass is a 1 to 2 because the other person is twice my weight. So I'm at 1 and the other person would be at 2. That would be their relative weight. So that's what we do here. We give them relative weight because these guys are tiny and very small numbers to work with. The electron, if the proton weighed 2,000 pounds, the electron is roughly about 1/10 of a pound. That's the weight difference between the proton and the electrons. So essentially, we give it a relative mass of 0, okay? Keeping in mind that, yes, it does have some mass, but it's very small. The proton's inside the nucleus. It has a letter P, superscript plus. It has a plus charge, and it has a relative mass of 1. And the neutron, which is a crucial part of the stability of the atom, is neutral in charge, okay? Hence the term neutron. It has a 0 charge, and it also has a relative mass of 1. Now, we're going to learn that neutrons is what what creates what are called isotopes. I'm sure you've heard of carbon dating, carbon 13, carbon 14, carbon 12. We have all of these carbon atoms that differ only by the number of neutrons. Okay, carbon 13 has an X amount of neutrons, carbon 12, an X amount, carbon 14, a certain amount, and we're going to learn about that too. Okay, now the important thing is this: the proton defines the element. On the periodic table, there's 118 elements. Okay. That number represents the number of protons. Hydrogen is element number 1, has 1 proton. Helium is element number 2, has 2 protons. We can lose neutrons and electrons all day long, lose or gain them, and we still have that element. Okay, carbon has 6 protons. That is carbon. It can lose electrons, it can gain electrons, it can gain neutrons or lose them, but it still has 6 protons. It is still carbon. That is what defines an element. The moment it picks up a proton, it becomes a different element, okay? So the proton defines what the element is. Atomic notation. All this is a way to write the symbol and the mass number and the atomic number. And we'll talk about this here. You know what? I'm gonna stop it here. 16. Let's stop chapter 4 here on slide 16. And then that way I'll give you time to get ready, spend the rest of the time if you need it, asking questions about the exam. If not, have a good weekend. Let me stop it and I will continue